Our last lesson of the semester will be about the Wilcoxon Mann Whitney test. This is going to be a statistical test for two independent populations where the t-test does not apply. So let's remind ourselves the characteristics of an unpaired t-test. So this is a parametric test, meaning that's used to estimate a parameter of a specific distribution. And it's distribution dependent, meaning that it depends on the sampling distribution being normal. And the t-test is good for analyzing the mean of a large sample or an underlying normal population. The downside to the t-test is that it does not apply to a small sample from a non-normal population. Now I'm going to describe the Wilcoxon-Mann-Whitney test, or sometimes called the Wilcoxon rank sum test. This is a non-parametric test. It does not estimate a parameter like the mean, but instead it compares the degree of separation between two distributions. It's a distribution-free test. It does not require that your population have a specific distribution. And it can be used for small sample sizes. But the downside is that it's not as powerful as the t-test. Now, the main idea of the Wilcoxon-Mann-Whitney test is that we're going to determine the significance of a test statistic, that test statistic we will label U sub S, that estimates the degree of separation between two samples of underlying distributions. So if I get a large test statistic, what it's going to represent is that there's little overlap between the samples. In other words, the distributions are different. If I get a small test statistic, that means there's going to be much overlap between the samples. And that means that we have indistinguishable distributions. So just like all of our other statistical tests, we're going to be looking for a large test statistic to tell us whether or not there's a small probability of rejecting the null hypothesis given that it's true. Now on this page, I've outlined the steps for doing the Wilcoxon-Mann-Whitney test. But instead of me reading through each one of these steps, I think we should look at an example. So the example that I would like to give is a question of asking, are there really more blue M&Ms in American packages of M&Ms? So below, you'll see a table of the number of observed blue M&Ms per American package, as well as the number of observed blue M&Ms from European packages. So when I spent a year in Heidelberg, I did some statistics with M&Ms with my class, and I discovered that there was something different about European packages of M&Ms than American packages of M&Ms. In particular, American packages of M&Ms tend to have more blue M&Ms. So I want to test this, so I opened up 12 packages of European M&Ms with my class, and we counted the number of blue M&Ms. When I got back to the United States, I opened up 10 packages of M&Ms from the United States, and I counted the number of blue M&Ms. And the question is the number of blue M&Ms different for American packages than it is for European packages? We have small sample sizes, right, 12 and 10, and there's no reason to believe that blue M&Ms, the number of blue M&Ms, has a normal distribution. So I'm going to use a Wilcoxon Mann Whitney test to compare these two samples. So my null hypothesis is that the number of blue M&Ms from European packages versus American packages is indistinguishable. It's the same. And the alternative is that the number of blue M&Ms from European packages is different from the number of M&Ms from American packages. So again, I have this sample of European M&Ms. When opening those packages, this is be a standard package of M&Ms. There were 5 blue ones in one package, then 6, 6, 7, and so forth and so on. And what I've done is I've arranged these samples from the least number of blue M&Ms to the largest number of blue M&Ms for both the European sample and the American sample. Now what I'm going to do is I'm going to take the column with the European sample of M&Ms and I'm going to compare each of the numbers in that column to the number of American blue M&Ms. And the way I'm going to do that is I'm going to ask the question, how many samples in the American column are less than the samples in the European column? So first, I will look at this European sample of just 5 blue M&Ms, and I'll look at the column of American M&Ms, blue M&Ms, and notice that there are no samples, there are no packages of M&Ms that have less than 5. So I will record a 0. I will do something similar when looking at 6. I will notice that there are none that have less than 6. And that is true for the next one that is 6. And then I will look at 7. So I have a package of M&Ms from Europe that had 7 M&Ms. And I'll notice that there's an equal number from a package from America that had 7 M&Ms. And since this is a tie, I will give that a score of 0.5. Okay, now there's a European package with 8 M&Ms, and I will notice that there is one smaller one than the 8. So 8 here, there's one American one that's smaller, that's 7. So I will put that there is one that is smaller. And that is true for each of the packages that had 8 M&Ms in it. Now, I will look at the package of M&Ms that had 10 blue M&Ms in it. And I will look at the American samples and notice that there was 1, 2 that were smaller, and then there were 2 that were tied. So the number that is smaller, I'll count as 1, 2, 2.5, 1, 2, 2.5, 3. So I'll count half for each tie. So there are 3 recorded as smaller. I'll do that, of course, for the next 10 as well. And then I will look at the sample that had 14 M&Ms, and I will now count how many are smaller in the American side. So here we have 1, 2, 3, 4, 5, 6, 7, 8, and then a half. So I'll count 8.5. Then for 16, I can count again 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's a tie there, so I will call that 9.5. I'm now going to add this column, and the sum of the numbers in this column is 28.5, and I'll give that a name. I'll call it K1. Okay, now we're going to do something similar. We're going to take all the samples of packages of M&Ms from the United States. And we're going to count how many packages of European M&Ms had less blue M&Ms. So I'm going to start with this 7, and I can count 1, 2, 3 and a half. So there are 3.5. And then I can move on to 9, and I can count 1, 2, 3, 4, 5, 6, 7, 8 that are less. Moving on to 10, well, I have 8, 8.5, 9 that are less. Then for 11, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that are less. And then for 12, there are also 10 that are less. For 13, there are 10 that are less. For 13, there are also 10 that are less. And then for 14, we get an added tie, so that's 10.5 that were less. And then for 16, I'll go through that count one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.5 that are less. Okay, so I'm now going to total up that column. I'm going to get 91.5. For completeness, I'm going to remark that there were 12 samples of European M&M bags and there were 10 samples of American M&M bags. Okay, so I have counted the number of observations in the other list that are smaller, and I've noted that the same size counts as a half. So anytime I saw that there was the same size, I got a half. I summed each column to find K1 and K2. They were 28.5 and 91.5. And then I need to check my work. So I'm going to verify that K1 plus K2 has to equal N1 times N2. So if I add K1 plus K2, 28.5 plus 91.5, I get 120, and that is indeed 12 times 10. Now the test statistic, U sub S, is actually the larger of K1 and K2. In this case, 91.5. That'll be my test statistic. Now, the procedure for calculating the p-values is a bit complicated, but I will give you some insight into it in a moment. But normally what you would do is you would look up this test statistic, 91.5, in a table. So I'm going to go to the Wilcoxon, Mann, Whitney table. And you'll notice that the Wilcoxon, Mann, Whitney table that I've provided and that you should download from courses has two columns on the left, N and N prime. You should think of these as being N1 and N2. And in our case, N1, the larger N, is 12. So we will go through this table until we get to N being 12. Then N prime, which is going to be our N2, was 10. That was the size of our other sample. So we have 12 and 10. That tells me which row I need to look at. Then the numbers in bold are possible test statistics. And the numbers in italics are the p-values that would go with those test statistics. Okay, so I'll notice that my test statistic was 91.5. That's between the 91 and the 94. And that tells us our p-value is between 0.025 and 0.043. Another way to read this chart is that if you have a test statistic that is to the right of one of these given test statistics, like we do right here, then you can reject the null hypothesis with this alpha value, 0.05. Okay? But I'm going to be able to say that my p-value is between 0.025 and 0.043. So here it's between 0.025, and 0.043. So yes, we can reject the null hypothesis. We can conclude that the number of blue M&Ms from a European package of M&Ms is different from the number of blue M&Ms from an American package of M&Ms. And if you actually Google some of this on the M&M website, this is exactly what they're intending. The distribution of M&Ms is not equal for each of the colors of M&Ms in a package. There are 6 different colors, and they do not show up 1/6 of the time. They purposely try to have more blue M&Ms and also slightly more orange M&Ms. So blue is actually the most common M&M in an American package of M&Ms. You can think about what kind of test you could do with a package of M&Ms to determine if the distribution is not equal amongst the colors. Okay, so let's look into why this p-value makes sense or is what it is, and why the Wilcoxon, Mann, Whitney test, the procedure that we just went through, makes sense. So what I'm going to do is I'm going to consider a sample size where I have 5 from one group, and then I have a sample size of 4 from the other group. And instead of putting in the numbers, I'm just going to put in the arrangements of where these data points could occur. So for example, if K1 is 0, that would mean that all of the samples, and I'll put them all here, all the samples from the first group would have to be less than the samples from the second group. And then if K2 is 20, that would mean that below each of the samples in the second group, there are 5 samples in the first group below. So then K2 would be 5 plus 5 plus 5 plus 5, which would give you 20. So this is the arrangement you would have to have of your data. I don't have to have the specific values of the data, but I do understand how they're arranged. Now, if we had the opposite case, if K1 was 20, then that would mean that all 4 samples in the second group would have to be smaller than all 5 samples in the first group. That's how you would get K2 to be 0, because none of the samples in the first group are smaller than the ones in the second group. And then K1 would be 20 because underneath each one of these 5 samples, below each one of these 5 samples, are 4 samples from the other group. So I get 4 plus 4 plus 4 plus 4 plus 4, and that would give me 20. And so what you have is the 2 most extreme cases where all of the samples from one group are above all of the samples from the other group. And that would give you a maximum value for your test statistic of 20. Notice in both of these cases, U sub S is going to be 20, which is as large as it possibly could be. And of course, we would say in each of these 2 cases that samples 1 and 2 are distinguishable because 1 is clearly above the other. Now, when K1 equals 10 and K2 equals 10, that's when we have samples that are indistinguishable, as mixed as possible. So what I'm going to do is I'm going to arrange the samples so that between each of the samples in the first group is a sample in the second group. And then show you what I would compute for K1. So for K1, I would say, well, how many samples are below this guy? Well, 0. And then how many samples are below this guy? Oh, 1. How many samples are below that guy? 2. How many samples are below that guy? That's 3. And how many samples are below that guy? This guy right here, and that would be 4. Okay, and so that would give me a K1 that was 10. Okay, and then if I play the same game with the second group, then how many samples are below that one? 1, how many below that one? 2, how many below that one? 3, how many below that one? 4, and then you would get 10. And so with this arrangement, you would have that the two groups are as mixed as possible. They're as indistinguishable as possible. Our test statistic would be as small as possible. It would be 10. And so these diagrams show that a large test statistic, U sub S, corresponds to little overlap between the samples. Okay, so where do the p-values come from? Well, what we have to ask is, what is the probability that U sub S equals 20, given that the null hypothesis is true? Okay, given that the samples are indistinguishable. Well, we can think about that as the probability of getting one of two arrangements. So if US is equal to 20, that's going to be the probability that K1 equals 0 and K2 equals 20, right? Plus the probability that K1 equals 20 and K2 equals 0. Well, notice that these two probabilities should probably be the same, because there shouldn't be any difference between if I label one of the groups group 1 and one of the groups group 2. So this is really 2 times the probability that K1 is 0 and K2 is 20. Okay, well, that's 2 times. Now, what's the probability that K1 is 0 and K2 is 20? Well, there's only one arrangement. Okay, there's only one arrangement in which K1 is 0 and K2 is 20. We saw that up here. It's this arrangement right here where K1 is 0 and K2 is 20. That's the only way we can arrange the data points and get that result. But what is the total number of ways that I can arrange these data points? Let's think about that for a second. Let's go kind of back to this diagram. Essentially, what I have is 9 different positions. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 different positions. And then what I have to do is decide what goes in those positions. Do I put Y1 in this first position so that it's the smallest? And then maybe Y1 again, and then Y2, and then Y1, Y2, Y2, Y1, Y2, Y1. That's an arrangement that I can have. Okay, that would look like, say, the first 2 data points from Y1, then a Y2, then Y1, Y2, Y2, Y1, Y2, Y1. So I'm asking, if I have 9 objects total, how many ways can I arrange them so 5 of them are in one position and 4 are in the other? So 5 of them are in one group, 4 of them are in the other. So you should remember this kind of problem from counting. In fact, the number of ways that I can arrange this is, so in other words, to take 9 different positions and choose 5 of them to come from group 1 and 4 of them to come from group 2, that is a combination. So we could do 9 choose 5 or 9 choose 4, whichever you like. So you can even think about this as the 2 as being the number of arrangements because truly what I have is that this is one of the arrangements and this is the other arrangement that would give me that US is equal to 20. Okay, so now I have the probability. It's one arrangement out of 9 choose 5. Okay, so that's 2 out of 126, okay, which is approximately 0.0159. Okay, so that the probability of U sub s equaling 20, given our null hypothesis, is going to be 2 out of 126, or 0.0159. That would be our p-value. Now, let's look at the chart and see what I get for that particular instance. So if I go back to the chart, I'm in the position where I've got 5 for the first group, 4 for the second. If I have a test statistic of 20, notice that's 0.016, which we are comparing to 0.0159. So that does work with the chart. Okay, so in order to compute these probabilities, you'd have to do a bunch of these calculations where we're trying to figure out the number of arrangements that fit with that particular test statistic over the total number of arrangements. Okay, I do want to warn you that the p-values in the Wilcox-Mann-Whitney table are assuming no ties. Otherwise, it becomes a little bit more difficult to calculate those probabilities with those arrangements. The p-values are approximate if there are a few number of ties. And the p-values definitely need to be modified if there are many ties.